Hello everybody and welcome back to our parallel programming and computer architecture class. This is the Unit 7 of the parallel programming class, and we have started working with the CUDA programming model. And so you have seen the basics of how you can write programs with CUDA. And last time we discussed several different mechanisms and communication patterns that we can utilize between threads of operation that work on our data. And then we discussed how these work. So in this unit, we're going to start working on looking at the several layers of memory models that CUDA gives us as programmers, and how we can utilize them to efficiently program in parallel. So as you remember, really quickly from the previous unit of our parallel programming, we discussed several different aspects, several different patterns that could be extracted from depending on the problem that we're trying to address, and then reformat the problem that we have in terms of one or more of these patterns to be able to create a communication that can go over and happen between the threads of operation that we're running in parallel, with the goal of completing the task at hand. So to categorize these patterns of communication, we have a bunch of data as the input, and from that input, we're interested in creating some form of an output. So if you look at this, then we may end up with a relationship between the input and output data that is a one-to-one relationship, meaning that for each element in the input, we want to create an element in the output. We talked about two operations that we can use, or rather two patterns that we can utilize here, and those one-to-one operations are map or the transpose operation. The difference between map and transpose is that in the map operation, when you have an input data pattern and you want to create an output pattern, you basically create for each input pattern one output pattern, but essentially the relationship between the patterns and the order of the patterns stay the same. With the transpose operation, we discussed, for example, in a matrix or an array format, a two-dimensional array format, we may have the data in some order and we want to reorder this data in some other order. So for example, if you have your data in the row major order, but you wanted the data to be in the column major order, you perform a transpose on the operation. So basically the data number 1, 2, 3, 4, 5, 6 in the transpose operation would go in the column order. Like so, and we call this a transpose operation. Still, the two operations are one-to-one operations. For each element of the input, we create one element in the output, but the order in the transpose will be different than the order of the map operation. If you have the relationship between your input and output data to be in a many-to-one operation, meaning that for each element of the output, you gather the information from many elements in the input, then that pattern of communication we discussed is a gather operation. An example of the gather operation was, for example, in terms of the image filtering. And in fact, your programming assignment is going to be in this form. If you wanted to, for example, for each element of the input, if you wanted that to be the sum or the average of all the neighboring elements, you gather the information from all the neighbors, and then you create one element in the output. That's a gather operation. The scatter operation is the opposite. When for each element of the input, you want to scatter its values across multiple elements in the output. So that's a one-to-many operation. We said that we can reformat, for example, a filtering application or an averaging application in the form of a scatter operation as well as a gather operation. when you have your patterns that are many to one, they follow a specific kind of temporal or spatial pattern. Um, you can also reform that operation and consider that as a stencil operation. And we said, for example, if you have an array, a neighborhood that's in a four connected neighbor as opposed to the entire Moore pattern, then you basically apply a stencil and you gather the information from multiple elements, but with a specific kind of weighting applied to them, or or a specific relationship between the many to one gather that you have, and we call that a stencil operation. Two elements we haven't discussed so far, or rather three different kinds of communication patterns we haven't discussed so far. We will talk about them later. They're in the form of all to one. We call it a reduce operation, and all to all. Sort and scan operations are all to all operations. We discussed this in Unit 8 or maybe Unit 9 when we talk about GPU algorithms. So, for example, in a reduce operation, you basically, for example, if you wanted to sum all the elements and store them in one element, then that would be an all to all. And in terms of sort and scan, so for example, if you have an element that is in some order and then you want to reorder this element or this array, so you would have an all to all operation. So the sort and scan operations are going to be in that form. So now that we have these patterns of operation, we would like to look at our programming model and see how things are organized in terms of both hardware and software that we have. And then we'll try to see what kind of memory we have at our disposal and how we can utilize this memory to be able to efficiently program these patterns of communication. To be able to answer that question, how can we efficiently program or rather implement our parallel programming for a specific application, given these patterns of communications that we have seen so far, we need to look at our programming model. The way that our GPU hardware is organized and allows us to write our programs in parallel is by dividing our program into smaller computational models. And those smaller computational models are called kernels. And what we can consider these kernels as a unit of operation, and this unit of operation could be as simple as just storing a number in an element, or as complex as creating a very, very complicated mathematical equation. But it's a unit of operation, or sets of mathematical operations. But this is essentially a unit of operation that when we invoke, we can tell our GPU how many of these units of operations we want run in parallel, and how we want these units of operations to be run in relation with each other. We call each of those units of operation after they're invoked a thread of operation. So our kernels will run as threads, and then each threads come in a spatial packaging that we call them blocks. So threads will come in bundles of blocks. So if I were to run my kernels, then each function as kernel is going to be replicated. So all these arrays are going to be my threads. So each of these arrays is a replication of my kernel function. Each of them will have a unique ID, and they're going to be packed within blocks of operation. And we have seen these splitting, or rather bundling of our elements before in the last two units. Now, when I talk about kernel, I mean the entire bundle of threads of blocks. This is going to be my kernel. Each thread is going to be a replication of my kernel function. Let's change the color. So each thread is going to be a replication of my kernel function. And then what I can do is that I can say, well, what I want you to do, kernel number 1, I want you to have each 3 elements wrapped in a package, and then the next 3 elements wrapped in it, or next 3 threads wrapped in another package, next 3 threads wrapped in another package, and next 3 threads wrapped in another package. And I want to call that each of these packages, individual packages within my kernel, the entire grid. So this is basically my kernel grid, and we call these individuals blocks. So if I wanted 3 blocks with 3 threads each to run another function, I basically could have done that. So if I create a function foo, and that would be my kernel, then I can run 3 blocks in this relationship, spatial relationship, and then in each of those blocks in the right hand side picture I have 3 threads to run. Now when you look at this, you'll notice that each of these threads will have a thread index. So thread index for this guy is going to be 0, 1, and 2. Now within the next block, threads are going to have 0, 0, 1, 2. And within the next block, each thread is going to have 0, 1, 2 as their thread index. Now since these are one-dimensional, these are going to be essentially the x dimensions of my threads, right? So if I had multi-dimensional threads, so if I had a block that had threads like this, then each of these threads will have an x and a y ID, a 2-dimensional ID. If I had a 3-dimensional thread block, then what I would have essentially, so if this were a 3-dimensional thread block, so threads would be kind of like that, then each of these threads would have an x and a y and a z as their thread indices. Each of these blocks then also will have a block index. So here I'm going to have a block index dot x and dot y. Because now in this case I have 2-dimensional threads, blocks, same here. So each of these blocks will have 2 dimensions, a dot x and a dot y dimension. So for example, for this first one it's going to be 0, 0. For this one it's going to be 0, 1. For this one is going to be 1, 0 and 1, comma 1 for my thread blocks. Now how is this going to work? Remember that you have a graphics card, and when you basically hand over these kernels to the graphics card, you say, well, graphics card, what I want you to do is take this function and I want you to run these many blocks with these many threads in each block. So what happens? What does your CUDA capable graphics card give you, or rather guarantees that it would do? There are certain things, there are very few things that CUDA guarantees, and this is actually going to have huge implications in terms of how your processing will work. First off, the first important guarantee is that CUDA makes is that all threads in a block run on the same streaming multiprocessor at the same time. What that means is that when you specify a block size, and as I said earlier, graphics cards would allow you up to 1024 or 2048 or 512 threads as a maximum number of threads, depending on how big your GPU is. This is essentially guaranteeing that if you run a block of threads with so many threads in it, all of these threads within that block are going to be assigned and allocated on the same streaming multiprocessor. The most important implication of this this guarantee is that since all of these threads are going to be invoked within a block on the same streaming multiprocessor, they would have access to the same memory units. So if you needed some threads to communicate with each other efficiently, then put those threads that need to communicate with each other within the same block. So that's one important implication for you right there. The second implication is that all of the blocks in a kernel must finish before any other block from any other kernel is allocated and associated to your program, or to your GPU. What that means is that if you have a program that needs to be split in multiple kernels, you need to remember that the kernels will be serialized when it comes the time to program your code. So if you have in a kernel that's happening before another kernel a thread or a bunch of threads that are going to take a long time, although the rest of the threads may be finished and your GPU may be ready to take on the next kernel for operation, it has to wait until the previous kernel is completely finished. So you cannot parallelize kernels with each other. So that's the second implication here, and that is that you need to associate all of the parallelization that you need to do within the same kernel. And if there are certain sequencing in your program, and those certain sequencing are the ones that you can actually enforce in terms of splitting. The bad news was that you cannot run multiple kernels at the same time. The good news is that if you have a certain part of the process that needs to be ordered, going through different kernels makes the ordering possible for you. So if you have certain areas of the program that needs to wait on another area of the program, then you could make two kernels. The first one will run first, and then the second one will have to wait until the first one finishes. And if that was an order inherent to the program that you were trying to solve, this blocking of the kernels, or rather splitting of the kernels, will make sure that the order would be preserved in that sense. So these are the two implications here, that all blocks, all threads within a block will be assigned within the same streaming multiprocessor, and all blocks within a kernel must finish before any other kernel is invoked and run on your GPU. So how does that all work with memory? And here's what I want to start to talk about memory. And as a programmer, a very, very important part of your life as a programmer is going to be essentially consciously or unconsciously working with memory. And the more you know about how you work with memory, the more efficient programs that you can create. And it's no different when you are attempting to write parallel programs. In fact, working and handling memory when you're writing parallel programs is a lot more crucial for you to understand and to be able to work with. So to be able to address that question, we know that a GPU is made of a bunch of streaming multiprocessors. So you have a bunch of streaming multiprocessors that essentially are like a core of a CPU. And if you look inside of each of these streaming multiprocessors, you're going to basically look and see several kinds of memory hierarchies that are interconnected with each other. The top level of your memory hierarchy is your global memory. The global memory is like the RAM of your CPU. Same concept applies on your GPU. So each of streaming multiprocessors will have access to the same global memory. So all of your streaming multiprocessor would be plugged into this global memory, or your graphic RAM or video RAM or whatever the manufacturers call them. The next level of hierarchy within your streaming multiprocessor is your level 2 cache. The level 2 cache is a faster memory unit available and accessible to your streaming multiprocessor, but it is much, much smaller than the global memory. So whenever you have temporal or spatial proximity in terms of accessing your data, that data is going to be stored within the cache. And all the concepts of cache that applies to cache in CPU applies to level 2 cache on the streaming multiprocessors as well. Most streaming multiprocessors have onboard level 1 cache, which is much faster, but also has a very, very, very small unit of memory that you will have access to in order essentially to speed up some of your memory read and memory write. Each streaming multiprocessor will have a texture memory and a constant memory. As we talked earlier, texture and constant memory are effectively read-only memory units that are kind of views of the global memory. So whenever you wanted to deal with, and these are basically the memory units that are created within your streaming multiprocessors specifically to target certain aspects. For example, if you wanted to have a bunch of constants, for example, a matrix that is your projection matrix, for example, for your camera, whose contents are not going to be changing much, but they would have huge implications in terms of calculation of where the vertices end up being. You would basically store them in a specific memory that's much faster to access, and since the data is not going to change much once you load it once, then you can utilize it for the entire process. Same with the texture memory. Most of the time textures are basically bitmaps that won't change over time. And so in order to speed up the process of texture calculation, you just store them up into the texture memory once, and then you let your processing at certain iteration go over the texture memory and perform calculations. And this is basically these two specialized kinds of memory are at your disposal to use. So if you have an application that could utilize texture or constant memory, you'd get a lot of speed up. But then again, the caveat is that these two memory units are read-only, and they can essentially be associated as views of the global memory. And these are all um, connected to your streaming multiprocessors. The next level of operation is or memory that we have at our disposal is called the shared memory. Shared memory is a chunk of memory that's on board with each streaming multiprocessor, and it is a much faster memory unit than global memory, but also we need to remember that since this is hosted on a streaming multiprocessor, it's going to be smaller in terms of its size. And we'll see shared memory and its usage in patterns of communication. Now, as you may have guessed, the shared memory is that part of the memory that all threads within a block will have access to, and they'll be able to share. We'll get to this a little bit later. And finally, when it comes to your streaming multiprocessor, as if you remember from our conversation and discussion on your graphics processing units, each of streaming multiprocessors is broken down into a set of simpler processors or specialized processors. And these specialized processors will have access to both your shared memory through your symmetric multiprocessor, as well as your register files. Register files are essentially a set of 256 bytes or 512 bytes of specialized, very, very high-speed memory units that are available for fast operations. For example, if you wanted to multiply two units, one of them is going to be stored in the streaming in the register file. The other one is going to be fetched out of the memory, placed in another register file. The multiplication is going to happen to them, and this result is going to be stored in one of those registers in the register file. And so usually when it comes to your programming, you don't really get down to the level of manipulating your register files. This is essentially the part that we usually, most of the time, do not even touch at all, unless you want to do very, very hardcore ninja programming in which you essentially would want to manipulate the registers directly. But we will not get into that concept. So a lot of the programming that we'll do is going to be concerned and concentrated around shared memory and manipulation of the shared memory. Some work with constant and texture memory, and your global memory, which is essentially the kinds of things that we have done so far. All right, now that we talked about the architecture of our CUDA-capable graphics processing units or GPUs, and we talked about how or the kinds of things that the CUDA guarantees and the kinds of things that it doesn't, let's take a look at how that happens in reality. Now again, when I'm talking about programming, I cannot even emphasize this concept enough that programming is nothing but working with memory units. So even every single line of code that you write, it is a location in memory, either code memory or data memory that is going to be executed. When you look at that, then the CUDA model becomes very, very easy in terms of its understanding in memory. When you're running a kernel and you invoke this kernel with a set of threads that are organized in the form of thread blocks that fill a grid to be executed in your GPU, if you look at every single thread in the execution of your code, or in terms of the CUDA model, each thread of operation is essentially going to be effectively a function that is composed of a set of execution code, and call that I point it out with this arrows, and sometimes I draw a wiggly arrow, and this function individually if you were to look at it as just one individual function, will have access to its own local memory. So each thread will have access to a local memory. And the local memory are, and I will talk about these in code, are any memory units that you declare and define within the kernel function, or the parameters that you pass to this function by value. Those are all going to be within its own local memory. So for example, when you're writing, like if your kernel had a for loop, so for int I equals 0 to say I less than 100. If you had a character, for example, character my name, for example, that you associate within the function of the thread, these are all going to be referred to as its own local memory. That being said, each thread will have direct access to the global memory, and those accesses come in the form of the pointers that you pass, this basically the data pointers that you pass to the function as the thread. And those will be associated within or accessed from the global memory. Then when you're running a thread, basically, or invoking a kernel, and you associate certain threads to be allocated within the same block, then the entire threads within that block, each of them will have their own little individual local memory copies that they have access to. They all have access to global memory, but all of them will also have access to a smaller memory unit that is available to that block, and it's called the shared memory. So all these threads that are within the same block, they are going to have access to the shared memory as well as to the global memory individually. Now finally, when you're running multiple thread blocks as a part of the invocation of your kernels, then each of those threads within the blocks will have access to their own local memory, of course. They all have access to the shared memory of each other within their own blocks. And then all of these thread blocks effectively, independently, will have access to the global memory. Both read and write access to the global memory. So this is how your threads can communicate with each other. Each thread will be able to create a local memory for its own use, which other threads will have no access to. So if you wanted data not to be shared, that would be happening over the local memory of the thread. Threads within a block have access to the shared memory of that block, and each block will have a copy of its own shared memory to which its own threads will have access to. So that's a piece of memory that all these threads within the thread block can communicate to each other through. They all can write into it and they all can read from it. And all the blocks that are invoked will have access to the global memory. So if there's certain needs of communicating between blocks, that can be happening over the global memory accesses. And of course, everything that we talk about so far is on the GPU. So basically, the threads in their local memory, the threads in their blocks and the shared memory, and the global memory are all on the GPU. And of course, there is always the host memory, that's the RAM of your computer, that only the CPU has access to, and the GPU will have access to through the PCIe Express bus, and we will see later on how your threads can access the host memory directly. So when we talk about the host memory, we're basically effectively talking about the piece of memory that's primarily accessible and workable through the CPU itself or the host itself. And the global memory is essentially the memory on the device. And most of the time when threads work on some piece of data, it is most of the time in the form of a bunch of data that transfers from the host memory into the global memory. Then threads will work on it, either as a part of a global memory that's shared between all the thread blocks, or parts of it that are going to be read and written into the shared memory to which all your threads will have access to within a block. And then the part when your process is done, then the data is going to be transferred back to the host memory. So CUDA memcopy is going to be the code that you run to be able to transfer data between the host memory and the global memory of your GPU. So from this point on, we now know that threads will have access to each other's data if they are located within the same block. And we know that we can access that um, part of memory through a piece of code. We haven't talked about it yet, but we'll see it soon enough. Actually, let me just write it down. If you wanted to create an associate a memory unit that is shared between threads within the block, you basically augment it with the word shared underscore underscore on both sides of it. So, for example, if I have a kernel, let's say I'm creating a void kernel, and then I can use a local variable. That would be my local variable that each thread will have access to. And if I wanted to have a copy of shared memory from all of the threads within each block to access it, I'd tag it with the word int shared int b. Then this piece of code b is going to be allocated in the shared memory, and all of the copies of my kernel that are within a block will have access to the same copy of b in the memory unit that they can work with. So my threads can work with their own data as a local variable, or with each other's data through the shared memory. Right? So if you tag a piece of memory, a variable or an array, or a pointer as shared, then all of the threads within a block will have access to. However, there's a problem. The problem is that since all threads within that the kernel within the block will have access to this piece of code, there is going to be collision happening. For example, if I have a kernel and I say int a equals that, and then shared b, and then I say b equals thread index, right? Thread index.x. Now, the problem is that if I run this as a kernel with one block and 300 threads, then the problem is the fact that all of the threads will have access to B, and all of them want to write their thread index into B. So what is going to be B? Since I have 300 elements trying to read and access this memory unit, I will have eventually a collision happening in there, and I would have to resolve that problem. So the problem of collision is there. How can I solve this solution? Specifically with this problem that I have right here, I really can't do anything to this piece of code, but effectively the idea is to synchronize my threads. Basically to hold on, to have some threads who are running ahead of the others before there's a piece of code that needs to be run by all threads. And if I want all threads to be able to start at the same point in time, the only means for me to be able to do that is through synchronization. So synchronization is one of the fundamental issues in parallel processing, and especially when we have shared memory accesses, when we have a part of memory that all of the threads will have access to, and they want to work with each other to be able to solve and address the specific problem that we're working with. Synchronization will be an essential component here. The simplest form that we can synchronize our threads to work and to cooperate is through what we call a barrier synchronization. What we can do is you can specify a point in the program for all the threads to halt and wait for others to finish their job, whatever they're doing, to reach that point in code, and then to start from that point all together again. And so that is essentially my barrier. So for example, let's say that in the previous piece of code that I wrote, I have a kernel and I have thread number 0, thread number 1, and thread number 2. They're all within the same block as you see here, and they're all going to take their own path to run. So thread number 0, this block, this black arrow, is basically going slow. The next thread may be going faster. The next thread, the green thread, may be going slower than the second one, but faster than the first one. And so each of these are going to execute some lines of code. So in their execution time, for example, if you specify the piece of code that they're running at, so for example, at any given time, if you look at the code, basically something like this is going to happen, and then and so forth. So your lines of code are happening, and so the threads are basically taking their time going through the lines of code. So if I wanted all the threads to wait at specifically this point in time before they start executing the rest of the code, I basically can implement that as a barrier. And I'll show you an example of how this works. So by the time you see the thread number one, or the red, reaches the barrier, it's going to wait. Then thread green is going to reach the barrier, it's going to wait. Then thread black is going to reach the barrier, it's going to wait. And at that point, when everybody's reached the barrier, then I release the barrier. So now everybody is ready to move forward, and this time I will have no control over who's going to start first, or how fast they're going to go. Of course, I can control that within code, but beyond that, it's associated on the hardware of your GPU. So in this particular example, for example, then the green thread started first, and then the black thread, and then the red thread after the synchronization barrier was reached by all threads. So this is basically a visual look as to how you can work with your code to make synchronizations in terms of execution of your threads when the need arises to be able to address the problem of threads colliding with each other or working with wrong data. Let's show you an example of this. How can we use shared memory through an example and see how we can make this work properly? The problem I'm trying to address here, and I'm posing it to you, is this. Let's suppose that we have 128 threads, and that we want to run these threads in parallel. What we want to do is we want first each thread to access a shared location in memory, and I'm going to call that shared location shared int my array 128. Basically, I'm allocating 128 memory units, 0 through 127, in shared memory. So all my threads will have access to it. And then I want to basically shift these elements one to the left. So the first thing I'm going to do is I'm going to basically create a shared memory with shared keyword int my array. Then I'm going to ask each thread to write their own index into their own memory location. So I use the index I, and I say if index I is equal to thread index.x, then write into the array at location index the number index. So thread number 0 is going to write 0 here. Thread number 1 is going to write 1 here. Thread number 2 is going to write 2 here. And thread number 126 and thread number 127 are going to be writing 126 and 127 into the last portions, last 2 bytes of this memory. Then what I will do is that I'll look at each index, and then I'll ask each thread to look at the index of the next element and store it into their own index. So basically what I'm doing next in this line of code is I'm asking, hey, thread number 0, look at whatever thread number 1 has and write it, or whatever is in location number 1, and write it into your location. So basically, effectively, copy 1 into the element 0, 2 into element 1, 3 into element, and 127 into element 126. And in order not to step out of my boundary, I'm going to stop at element 126. So I'm not going to do that for element 127. So element 127, or rather thread 127, is not going to do anything. Now my question to you is that, is this going to work? And if not, why not? Okay, If you may have noticed, the answer to the question I asked earlier is that yes, this program is not going to quite work as we expected. Now, just a point of caution here. If you write this very simplistic program with shared memory and a block of threads and 128 threads, the chances are you're going to get a reasonable result. And whenever you run this program, probably. The chances of this program not really working and doing what you expect it to do is going to be very little because of the data is being so small. And the operations we're performing here are very simplistic operations. So the thread race conditions that I'm going to explain here is going to be unlikely with this small data size. But the problem is that as the data grows and the operations that we're performing grow, this program, the simple way of us writing it is not going to work. Let me explain a little bit about the components of this program, and then I'm going to tell you what is happening here. So what I'm writing here is I'm writing a kernel that then I would invoke a bunch of it over in one block. So when I'm executing this program, I'm going to execute it as one block and say 128 threads in that block. And in each of these threads, I'm creating a shared memory array of integers, and it's going to have 128 elements in it. And then each thread is going to calculate its own index by looking at thread index.x, and then write its index into the shared array, which is here. Actually, here I called it my array. So let's correct this. So this is going to be my array. So it's going to write 0, 1, 2, 3, and so on. And then I'm asking each thread to look at its neighbor value from the shared memory and then store its rightmost neighbor, the content of its rightmost neighbor, into the location, its location in the array. So ideally, what I'm hoping that this accomplishes is that thread number 0 comes in and stores 0 in element number 0. And same with thread number 1 to store 1 in element 1, and thread number 2 to store 2 in element number 2, and so forth. And then when that happens, then for thread number 0 to look into whatever thread number 1 has written and then store that content into element number 0. So ideally, thread number 0 first stores 0, then looks at whatever thread number 1 has written, and then stores that value into its location. So basically, two things happens. Thread number 0 first writes 0 into index 0, and then looks at array location at 1, and whatever value is there, which we were hoping that it would be 1, to store that into its element number 0. And we're hoping that this happens over all elements. There's one slight problem, and that is I assumed that by the time thread number 0 goes here and looks at array at location 1, I assumed that thread number 1 has written 1 into its location, or the array location 1. What if when thread number 1 was executing, something happened, and then compute unit or processing unit that was handling the execution of thread number 1 was delayed a little bit. So if thread number 1 is delayed, let's say that thread number 1 is delayed at before the execution here, and thread number 0 had executed this and had gone on to execute this location, then the reading that it's doing from array at location 1 is not going to be valid because element number 1, thread number 1, has not finished writing into element number 1. And so I might be reading some nonsense number from element number 1 because thread number 1 has not finished its operation. And this is the problem of race conditions. Notice here my thread number 0 or thread number I is looking at element at location I plus 1 and storing in element I, where the location of element I plus 1 is going to be bound to thread I plus 1 here. So this three conditions here, writing of the threads, reading of the threads, and then writing of the threads, basically these three elements, two writes and one read right here, are going to be race conditions because multiple threads are executing at the same time, and we would not know which thread finished before or which thread is at which location of its own code. Remember that each of these 4 lines of code is going to be replicated. For each thread, you're going to have a replication of this line of code, but you will not have control over how fast each thread goes through these lines of code. And these are the race conditions that we are talking about when we are working with shared memory and thread communication. To solve this problem, we need to add barriers in our code. Notice that the problem that I had and I just explained was that each thread is looking at its next door neighbor, reading its value, and storing it into its own location. But this read and write operation is bound to the previous line of code, which basically we want them to happen sequentially. We want each line of code to execute when every other thread has finished their own line of code up to that point. Basically, my problem that I may encounter is that if my threads are running at different various speeds, right? And if these threads are communicating with each other, the pieces, the lines of code that communication is crucial, the lines of code that will encounter race conditions, we want them to be synchronized. We want to put barriers so that no thread will go beyond that barrier before every other thread has reached that barrier. So the problem that I'm encountering is that there are certain areas in this code that threads need to wait for each other before we move on. Where are those areas and how many barriers do we need to add into this code to make sure that this code will work? I'll give you a few minutes to think about it, and then I'll talk about it. So, let's see how we can make this work. Now, the problem that I'm encountering, as I said, is that each thread is writing a value in its location and then moving on to read somebody else's location and store their value into their own location. The problem that I'm encountering is actually 3 race conditions. One race condition is right here. And that race condition is basically threads writing. The next race condition is actually a twofold condition here. I have 2 problems here. Each thread is reading a value from somewhere and writing it into somewhere else. So this actually in itself, it's 2 race conditions. And I call them race condition number 2 and race condition number 3. So the race condition number 2 is basically encountered when threads read values. And finally, last race condition is where the threads write. Some result somewhere. Basically what my problem is, which essentially effectively in my case I have a serial problem, and it has to be serialized because I want these numbers to shift one to the left. So before each number is finished, I want to make sure that all the previous numbers before it have been finished. So the first race condition is when every thread is writing stuff into the memory. I want to stop all threads there for everybody to have finished writing their values. Then I want threads to read values from their next door neighbor. And according to this, I want to stop all threads after everybody's read the values. Then I want everybody to write the next door neighbor that they just read into their location. So I want another race condition that happens over there. So race condition number 1 happens when threads are writing. Race condition number 2 happens when threads are reading next door neighbors. And third and last race condition happens when threads are now writing inside of their own code. So to fix this problem, I'm going to split this line of code into 2 pieces of code. So I'm going to basically add 2 brackets here, and then I'm going to create an int temp variable and make it equal to array +1, and then I make array add index to be equal to temp. To solve my problems, I'm going to use the keyword sync threads. So when threads write their stuff into their location, I synchronize my threads. So a barrier is going to be added here. So barrier number 1. Then when threads read values and put in the temporary variable, I put my second barrier. And finally, when threads wrote the temporary variable that they just read inside of their own location, I place my third barrier in code. This ensures that before each thread goes about writing their next door neighbor, we make sure that all threads have written and are done with writing their contents into the locations. Then before each thread writes inside of its own location, we want to make sure that all its neighbors have read its values. So we sync thread there after the read operation to make sure that all threads are also synchronized and they read the correct state-of-the-art finalized values from the next door neighbor. And finally, when threads write their values inside of their content, inside of their locations in the shared memory, we synchronize everybody so that we make sure that all threads have access to the up-to-date data and information from this point on in our code. So the way that our program works is that if we're working with just one singular thread and it's basically working with local memory, we will not really have much of a race condition because each thread's local memory belongs to its own execution, and no other thread will have access to its execution and local memory. So we can have each thread basically to take care of whatever they're doing with their own local memory without any hesitation and problem of race condition and conflicts. However, when you're working with shared memory, the good news with shared memory is that actually there are 2 pieces of good news. The first good news about shared memory is that it is a much faster block of memory. It's very small. It's 48 kilobytes in total that can be associated per streaming multiprocessor, but it's up to 4 times faster than accessing global memory, especially if you have threads that need to go around in the neighborhood and do a lot of calculation. If you keep doing that with the global memory, every read and write operation is going to have a hit into the global memory, which is very expensive and very slow compared to shared memory. So you pull that data off from the global memory into shared memory of your block, and then you perform your operation. This is called tiling. We talk about it in a little while. And essentially, you can do a lot faster with the shared memory. The problem is that since shared memory is shared, all threads will have access to it within the same block, and in that case, the race conditions become crucial. So since we have no control over the order of threads when the threads are being launched, as well as the execution speed of our threads, we cannot make sure that all threads will reach a point in code all at the same time or all at a certain kind of order. We need to add barriers. And in our case, we use sync threads by using this sync thread keyword, which is basically sync threads as a function after two underscores in our code. And so if we have threads that are running in parallel and we have no absolutely control over the order of these and the speed of these thread operations, we won't know which one is going to execute which line of code first and which one's going to be last. We basically synchronize the threads at a certain point in code when everybody needs to have their data submitted, so to speak, before anybody could proceed executing the program. And finally, when we work with global memory, each thread block or all of the threads in the block that belong to each kernel will execute and finish before any other kernel is executed. And so the thread communication between multiple kernels could happen and go over global memory, and we will be sure that there is an implicit synchronization between threads from different kernels. So if you have multiple kernels that are launched after another, the second kernel's threads will not run before all of the first kernel threads up here, this blue kernel, are executed and finished. So you can think of each kernel effectively having an implicit barrier at the end of its execution. So we will be sure that before these green threads belonging to the green kernel will have access to the global memory, all the threads from the blue kernel up here are going to be synchronized effectively. So this brings us to a very good idea as to what is CUDA. CUDA is actually a programming model that is built on a hierarchy of computational units that is our threads, our blocks of threads, and the grids that each kernel is going to be executed on, with their corresponding memory spaces, shared, local, and global. Shared memory are memory units that are associated with each streaming multiprocessor, and all threads within a block will have access to that same shared memory. Local memory is the local memory that is associated with each thread, and each thread can execute and work that local memory, and these are essentially on register memory units, and the global memory, which is shared between all the kernels and all the blocks and all the threads. And synchronization primitives, sync threads and barriers that we can add to our code to make sure about the data integrity of our program. So with that, we're going to next look at some examples and look at some memory examples in CUDA and see how shared memory, global memory, and local memory are accessed and work.